Hello. So I thank Valerie and Michelle for the opportunity to come to CERM and to speak. So I'm going to do 3 lectures, and it's actually going to be 3 lectures on 3 disjoint topics. The second lecture will be on connections of Golod-Shafarevich theorem to pattern avoidance. The third I intend to do on spreading out, which is a technique in algebraic geometry, but I'll discuss some of the lesser-known aspects of this technique. And my first is something that, I don't know, I hope it's very accessible. Well, when a talk is accessible, it can be boring to some people. So I'm not going to apologize for being boring, because life is boring a lot of the time. But this is something that I think is a notion that's interesting to study, but it hasn't really been looked at. So I hope maybe some people will find it interesting. So I'm going to start. And there's Boris. Okay. With K being a field, and A will be a K algebra. So of course I just mean that it's a ring with an embedding of K into A, such that the identity of K is the identity of A. And I'm going to talk about something that maybe some people know, maybe some people don't, but this is an old concept that goes back to Kaplansky and Omitzer. We say that A satisfies a polynomial identity and I'm going to say is PI for short if so kx1 through xt is the free algebra on D generator, so I think of this as just a polynomial ring where the variables don't commute. And I want to say that there's some number of variables and some non-zero polynomial such that at each specialization I get 0. So, of course, the prototypical example is, of course, a commutative ring. Which satisfies this identity. Another example, less well-known example, this is due to Wagner, not the composer, unfortunately, but still a famous identity, famous mathematician. We take A to be 2 by 2 matrices over C, where C is commutative. And it satisfies the identity x1, x2, x3 minus x3, x2 squared equals 0. You can give this question to your students, or if you're a student, I guess you can do it, but if you do it, they'll just plug in A, B, C, D, E, F, G, H, and just compute, and you can do it this way. There's another way to do it, which is to notice by the Cayley-Hamilton theorem, it says that if Y is a 2 by 2 matrix, then Y satisfies its characteristic polynomial. And you can check the linear term is the sum of the eigenvalues, and the product of the eigenvalues is the determinant. So you get this. And so what this says is that if I have a matrix of trace 0, then y squared is scalar, because this goes away. And now notice that if I plug in any 2 by 2 matrices, this guy is going to have trace 0, right? Because it's just AB minus BA. So its square is going to be central. It's going to be a scalar. So it's going to commute. Sort of fun. Oh, yeah, just some more preliminaries before we move on. And I will connect all this to automatic sequences and regular sequences very soon. Oops, that's not the microphone, that's good. We say that an identity so we'll say it's homogeneous if every monomial occurs with the same degree. With the same total degree. So for example, something like this is homogeneous of degree 3, and it's multilinear if in every monomial that occurs in F with non-zero coefficient we have each variable occurs exactly once. So it's a very fun exercise to show that if you satisfy a polynomial identity, then you actually satisfy a multilinear homogeneous identity. So I'll just write this as a fact. Oh, I don't want to erase. I want to do this. This feels like it's probably taking longer to me than it is to you, I guess. That's probably good enough, right? All right. So fact, if A is PI, well, that implies there exists a homogeneous multilinear identity. So that's just one of these facts that's not so hard to show. And the significance of satisfying a homogeneous multilinear identity is the following observation. So the following remark. If B is a K-spanning set for A, if I want to check that it satisfies a homogeneous multilinear identity, I just have to check evaluations in B. So to check that A satisfies a homogeneous multilinear identity F, it suffices check evaluations just on the spanning set. So it saves you some time. And this is an easy remark to see why. To see why, well, suppose I know all of these guys vanish, right? And I look at one of these evaluations. Then I know I can write my A1 as some linear combination of these BIs. And then because every variable occurs with degree 1, it's linear in each variable. It's multilinear. So that means I can break this up and then I can just go through variable by variable. And I get that this is a linear combination of these guys. Okay. I gave that as a question on an assignment, and all the students complained. But it's just pages and pages, but it comes out to a, I guess a degree 5 variable identity.
This fact is also applied to case finite?
What's this?
This fact, is it also applied to case finite?
This fact.
Yeah.
That's a good question. Maybe. I have to repeat the question. Does this fact apply if k is finite? I think it does. I know what you're thinking, though. I think it does, though. Because there is some Vandermonde, potentially, argument going on. What do you do with this board? You slide it up, and then I slide this board down, I guess, right? This fact is actually useful. A corollary of this fact is that if A is pi, then if I extend the scalars, is pi as well. Because I take my algebra, I know it satisfies a homogeneous multilinear identity, and it just suffices to check on a basis. But I know a basis here gives me a basis here, right? A k basis here corresponds to an f basis here in a natural way. So I get this. And in fact, there's another more general fact. There's a theorem due to Reg F if I have two k algebras that are pi, then this is pi. And of course, a field is always pi, so this is a more general fact. Okay, so I'm almost getting to the connection to automatic sequences. I hope this isn't too bad so far. So I'll just say some important identities. So the most important is this identity, Sn. And the way it's defined is it looks a bit like a determinant. So this is going to be the nth symmetric group. And I don't want to use Sn, unfortunately, so I use this. And what I do is it looks like a determinant, like I said. I take the sign of sigma, and I sum over all permutations of the variables. So notice each variable occurs with a degree exactly 1, and it has total degree n. So this is homogeneous multilinear. And there's a famous fact due to Ami Brown that says if A is a finitely generated PI algebra, that implies A satisfies Sn. And this needs finitely generated. Okay. So I'm finally ready to start getting to the connection with automatic sequences and regular sequences. Maybe I can do this and this. That's pretty good. And then this. That's good? Yeah. Here's a theorem. Some of you might know this theorem, but it's a wonderful theorem. If you don't know it, well, you're going to know it right now, I guess. So this is Levitsky. Amitser was Levitsky's grad student. And all it says is, let C be a commutative ring. Commutative ring. Then the ring of n by n matrices over C satisfies the 2nth standard identity and satisfies no smaller identity. So that's somehow the minimal identity for n by n matrices. Well, the way they proved this was the fact that this is multilinear. We just need to check it on a basis. So they look at the basis being the matrices Eij that have a 1 in the ijth entry and zeros everywhere else. And then you can think about what it means for a product to be non-zero, right? It means there's some consistency condition on the indices. And then it's basically a graph theoretic argument from there. There's other arguments. There's cohomological argument for this. There's a theorem, a quick proof using exterior algebras. There's many proofs of this.
Is S2 actually a generator of the idea of polynomial identities?
I don't think it is. I mean, there's a theorem that says you want to look in. Well, there is a theorem that says all identities are in some sense generated by Cayley-Hamilton theorem. So you can sort of deduce this from Cayley-Hamilton theorem. But I don't think if you just looked at the things Sn, like all identities that are implied by this, that it would give all of them necessarily. That's my feeling. Okay. So now I'm going to talk about the connection to automata, automatic sequences, and work of Burstel and Reitnauer. Oh, okay, that's good. I thought I put that too high. So this is old work of Burstel and Reitnauer that's maybe not so well known, but is So for me, I'm going to do things in a slightly unorthodox way. So I'm going to take k to be a natural number. Bigger than or equal to 2. The natural numbers will always include 0 for me. And rather than doing this thing with base k expansions where I have to worry about zeros at the beginning, I'm just going to to make me not have to worry about putting this caveat in all the time, I'm just going to instead work with the semi-group on the letters 1 through k, and I'll make a bijection here. Where the empty word goes to 0 and everything else goes like this. So it's not important. It's completely equivalent to the old way of doing it. It's just, I'd rather avoid having to talk about paddings with zeros and stuff like this. So Aleutian Chalet defined regular sequences. So a map so for the purposes of this talk, I'm only going to consider k-valued maps, but we can do this with any commutative ring, is k-regular so this is Aleutian Chalet's definition. If, well, instead of working with n, let me really think of it as a map on this free monoid, has the property that the maps so if I look for each word v, I can get a map f superscript v, which is just where its evaluation of a word u is just f at uv. So if I look at these maps, well, since they're images in k, I can add them, I can multiply them by k. It's a k vector space. If the maps fv have a finite dimensional span, a finite dimensional big K vector space. And this is a generalization of automatic, because automatic is really saying you only get finitely many maps, right? But now we're saying that they have finite dimensional span. I think I want to do this. Can I do this? No, I can't. Okay. All right. I'm not very good at these boards. Sorry about that. All right, that's great. So a theorem that people presumably know so being k-regular is equivalent to the following condition. There should be some integer d bigger than or equal to 1. Matrices A1, A, K, with entries in the big field, MDK, and vectors V and W that are column vectors such that if I want to know what f does to a word, there's this nice rule. I just take my word, and it corresponds to some product in the semigroup of matrices in a natural way. And then if I multiply it by this column vector, I get a column vector, and then I'm taking the inner product, the dot product, with some other vector w, so I get a scalar. And as a corollary, Burstel and Reutenauer prove something a little stronger than this, in fact, but this is what I'm going to focus on. We have this interesting shuffle property. Rather than write out a proof, because maybe you see why this is true, let me just say what's going on. F being regular means that I have an expression like this for d by d matrices. Levitsky theorem says that if I take a product of 2D matrices and shuffle them around, I'm going to get 0. So this really is, right? This guy really is W transpose AU where by A of a word, I mean the corresponding product of the A letters. So A12 will be A1, A2. And then, of course, if I shuffle this around, I can pull the W transpose out and the V out on the right, and I'm just getting the Levitsky thing. I should say one more thing. The span of this finite dimensional vector space, if we call that D, that's what's called the dimension of the kernel of F. This D here is the same as this D here, is the same as this D here. So they all correspond to one another. I should say that Burstel and Reutenauer actually gave a characterization of K regular. So being K regular is the same as having this property plus one extra property that basically says that if I look at F along powers of a word, it should satisfy linear recurrences in a nice way. But I won't make that precise. So what I'd like to talk about for my first talk is some concept that, like I said, I think might be interesting for someone to study maybe, and I'll say what I know about them. So a shuffled sequence. We say that F, so I'm really thinking of it as a map from the natural numbers to K, is K shuffled if there exists some n bigger than or equal to 1, such that such that basically I look at all possible ways of shuffling the intermediate n words, and I weight them by the sign of the permutation, and when I sum, I get 0. That's a k-shuffle sequence. I don't know what board to go on to. Let me do this. No. This. And let me just take the second one down. Hopefully that's okay. So for maps, so k-automatic maps are strictly contained in k-regular. So any of these questions where people ask, are these k-regular? And the answer is no, one can ask if they're k-shuffled. I want to say just that the inclusion is strict. In fact, you can show it's very strict. So there's a theorem due to Aleutian-Shallot that says that if f from n to z is k-regular, then there exists some d so that fn grows at most polynomially in n. And with k-shuffled maps, you can have arbitrary growth. In fact, if you just give me any integer sequence you like, a1, a2, a3, I can make a map that takes any word of this form to an and takes any word that's not of this form to 0. And it's not a hard exercise to show that this is shuffled, where I can take this n to be 4. But because an can be whatever I like, I can make it have arbitrary growth. So I know that the containment is strict. I want to show that there's at least some application of this, so let me just give an application, even if it's not such a wonderful application. By the way, I put all this in a chapter. Michel and Valerie are compiling a book for this conference, and we had to, no, we didn't have to, but some of us wrote chapters. So I wrote a chapter, some of it's going to be on this. So let me give you an example. In their book, Aleutian-Shallot on automatic sequences, they ask the following question. So they have a chapter on regular sequences that they defined, and one of their questions was this. Well, this was open when they wrote the book, and in around 2008, a guy named Yossi, a student of Falouche, I think, figured out a solution. But I want to point out that there's actually a nice way to do this by showing it's not shuffled. So how can we do this? One of the reasons they asked is because this function, the floor of log 2n, is actually a two-regular function. That's not hard to see. And so they were asking, really, what if I shift? Is it still two-regular? Well, if I do this, then notice f of n is always at least this, but it can never exceed this more than 1. So this is 0 or 1. And if I think about when is it 0 or 1, it's not hard to see what's going on. Notice that fn if I want to know when this is equal to 1, that's if and only if there exists an m so that I get this. And if I exponentiate, that's saying that there's some m so that I get this. And if I think about it, if I think about root 2, it has some binary expansion. I don't know what its binary expansion is, something like this, right? Then what this means is if and only if the base 2 expansion of n is pure lexicographically bigger than this right infinite word. Because if I think about it, if I'm pure lexicographically bigger, as I start reading left to right, at some point, maybe they agree, but at some point it's a little bigger. And when I multiply by root 2, it's going to take me beyond a power of 2 for this reason. So you can think about this. I think I'm just going to interchange. No? This. No? Sorry. Very confused. I don't even know what board this is anymore. This is, okay, there we go. So you can think about this, but this is the case. And if I think about the expansion of root 2, because it's irrational, what I know is that it has some prefix, u0, and then I can find w1, w2, wm. I can break it up into words so that I break it up into these words, this prefix of the binary expansion of root 2, in a way that it has this decreasing subsequence, pure lexicographically decreasing subsequence. Well, what I'm saying isn't quite right, but imagine if I replace wm by something just a little pure lexicographically bigger, but still smaller than wm minus 1, which I can do. Then what happens is this guy is 1, because it's pure lexicographically bigger than the expansion of root 2. But any permutation is going to have 0, because once I take a permutation, I've put something that's too small at the front. And so this goes below the expansion of root 2. So since this guy is 1 and all other permutations are 0, I can't have the shuffle property. Let me talk about some closure properties. And then I'm going to talk about some open questions that I think are interesting, and I'll try to explain why. So this is the last section. So the first is that if I take two shuffled properties, two shuffled sequences, then their sum and their product is shuffled. And I'll give a brief explanation why, because it's not so easy to see. And it uses this theorem of Regev that I mentioned. So I'll give a sketch of the proof. So here's a quick sketch of the proof. To my sequence F, so I'm going to think of F and G as being now maps on this monoid. And what I'm going to do is to F, I'm going to associate an algebra on, big K, on little k generators. And I'm going to mod out by an ideal, which I call IFF. And what is IFF? IFF is just the collection of words. So it's the collection of polynomials such that So I'm being a little deceitful here. These words are really on the alphabet x1 through xk. But in my head, I'm just thinking of x1 as being 1, and x2 as being 2, and xk as being k. So here, that's what I mean here. I don't want to put an algebra on 1 through k, right? On the numbers. So I'm really thinking of x1 as being 1 when I talk about this evaluation. So if you like, I can identify. And that's why in the shuffled property we put a u in the v, because that ensures that this is actually a two-sided ideal. So in the definition I gave of the shuffled property, I put a u and a v on the left and right, and that will actually guarantee that this is a two-sided ideal. And similarly, I can make an ideal I sub g. Now, here's the fact. Because F is shuffled, right, it satisfies some identity. So you can check that these algebras are actually PI. So the fact that F satisfies one of these shuffle identities gives me that this algebra satisfies a polynomial identity. That's just a routine calculation, but I don't want to spend too much time on it. And then there's a Regev's theorem. implies this algebra is pi, because it's a tensor product of two pi algebras. Well, any subalgebra of a pi algebra is pi, because it will satisfy the same identity. So if I look at the algebra generated by this guy, this is pi. Now, by Brown's theorem, this satisfies some standard identity. And what that will show is that this sequence, which is really the same as this sequence, satisfies some standard identity. And so then you get that FG satisfies some shuffle identity as well. Maybe that Prout sketch wasn't so good, and now that I think about it, but at the time it felt like it was going to be good. But the point is, it's not obvious that the product is shuffled, but it is. So it has this nice closure property. Another fact that's easier to prove that if I have two shuffled maps, I have a product, another product on words, which just goes as follows. I look at all ways of decomposing my word W as a prefix and a suffix. And then I just define it to be F-U-G-E. So one can prove that if F and G are k-shuffled, then under this product, k-shuffled becomes a ring. So the shuffled sequences are a ring with two natural products, one a commutative one, this Fn, and another a non-commutative product. So if I look at the shuffled sequences taking values in my field K, they form a non-commutative algebra under this product. And you can show some interesting things. It's a big ring. It has a free algebra on infinitely many variables. So it's a very big ring. Okay, so let me ask some open questions now. So here's one Jeff asked. If I have two k-shuffled sequences, does that imply that the Cauchy product So that's the first question. It's a nice question. I don't know the answer. Now I'd like to give a question I'm really interested in. I'm interested in that one, but I'm more interested in the next two questions. And these are my last two questions that I'll ask, I think. Yeah. just for simplicity, I'll assume I have a z-valued sequence. And suppose g of n is never 0 and it always divides f of n for every n. Does that imply Well, let me explain why I'm interested in this question. There's a famous theorem in number theory, the Hadamard quotient theorem, that says that if I have two functions f and g from n to z, say, that satisfy a linear recurrence, they each satisfy a linear recurrence, and suppose we have these two properties, then their quotient satisfies a linear recurrence. Aleutian Shalit asked the same thing for k-regular sequences. Now, it's a natural question to ask, in fact, because if you think about linear occurrences, they correspond to rational functions. And the Burstel-Reutenauer framework shows that regular functions correspond to non-commutative rational functions. So it's basically just asking for a non-commutative analog of the Hadamard quotient theorem. Now, if you use the Burstel and Reutenauer characterization of regular in terms of shuffled and other properties, the other property just comes down to verifying that to that the quotient satisfies that property comes down to just looking at the ordinary Hadamard quotient theorem for linear recurrences. So if you could answer this, you would in fact get the Aleutian Shalit question as well. So that's why I'm interested in this question. And then the final question is Grabham's. So if I have two natural numbers that are multiplicatively independent, and if f from n to, let's say, a field k is k shuffled and L shuffled, well, the ordinary Cobham theorem says if I'm k automatic and I'm L automatic, I should be eventually periodic. And if you go to regular sequences, the conclusion is that it satisfies a linear recurrence. And I believe the same conclusion should hold here. Does that imply f satisfies a linear recurrence? i.e., does there exist some d greater than or equal to 1? So that's the three questions I'm interested in. That's all I have to say today. Thank you.